Okay, let's dive right into this explainer. Today we're going on a fascinating journey, tracking exactly how power travels from a car's engine all the way to its wheels. We're going to pull back the metal skin of the vehicle and look at the hidden physics at work. To do this, we've got this absolutely gorgeous, cinematic 3D cutaway right here in our virtual scientific studio, giving us a perfect, close-up look at a metallic V8 engine block and its entire drivetrain.
Now, think about the core mechanical mystery we've got here. A standard V8 engine's crankshaft spins incredibly fast. Way too fast to just hook directly up to the wheels. I mean, if you did that, the engine would have absolutely no leverage to move a heavy car. It would literally just stall out immediately. So how on earth do we translate that raw, chaotic, high-speed rotational energy into smooth, controlled forward motion? Well, here's our blueprint for today. We'll quickly hit 1. The concept of torque. 2. The V8 engine block. 3. Transmissions and gearboxes. 4. Drive shafts and joints. And finally, 5. The differential. Let's get into it. Starting off with Section 1, the concept of torque. To truly grasp how this heavy machinery actually gets moving, we have to define what's flowing through all these metal components. You know, it's really easy to just throw around the word horsepower, but any automotive engineer will tell you that's only half the story. See, while an engine makes its maximum power at really high RPMs, cars actually rely on torque to get going. Torque is just a turning or twisting force. It acts exactly like mechanical leverage. When a vehicle is just sitting there, standing completely still, the engine simply can't develop enough torque on its own to overcome the immense, dead weight of that chassis. It needs a massive mechanical advantage to get thousands of pounds moving from a dead stop. And that takes us to Section 2, the V8 engine block. Looking closely at our 3D render, right at the absolute heart of the vehicle, we find the longitudinal V8 engine block. This is where the combustion of fuel and air creates that initial violent rotational force, slamming pistons down to spin the crankshaft. And from there, the energy follows an unbroken chain of rotating metal. It kicks off at the crankshaft, flows straight into the transmission, travels all the way down the length of the car through the drive shaft, and finally gets distributed out by the rear differential.
Which brings us to Section 3, transmissions and gearboxes.
So the transmission solves our very first major problem. It uses gear reduction to act as a lever, multiplying the engine's torque, so you can actually pull away from a curb smoothly. Inside an automatic transmission is this absolute marvel of engineering called a planetary gear set. It's like a giant dynamic metal puzzle. It changes output speed and torque by manipulating these interlocking components. You've got a sun gear right in the center, planet gears revolving around it held in place by a planet carrier, and an internal ring gear encasing the whole shebang. By just changing which of these parts is doing the driving, which is being driven, and which is locked in place, the transmission can completely alter the torque output. For example, if you hold this sun gear stationary in the center, and the ring gear drives the planet carrier, the output rotation slows way down, but the torque is heavily multiplied. That forward reduction is exactly what creates that massive surge of pulling power you feel pushing you back into your seat when you stomp on the gas pedal. Now, it's pretty fascinating to compare our longitudinal rear-wheel drive V8 layout with a front-wheel drive car. In our setup, the transmission sits right behind the engine, sending power all the way to the back tires. But in a front-wheel drive car, engineers have to cram the gearbox and the differential into a single tightly packed unit called a transaxle, and they mount it transversely or sideways right under the hood. It is an incredibly tight squeeze, and it totally changes the entire architecture of the driveline. Moving down the chain to Section 4, drive shafts and joints. Getting back to our rear-wheel drive V8, as that energy leaves the transmission and hits the drive shaft, it instantly faces a whole new hurdle. The rear axle isn't just sitting still, it's constantly bouncing up and down over potholes and bumps. That means the angle between the transmission and the rear wheels is changing every single second. The crucial fix for this is the universal joint, or U-joint. It basically acts as a super strong, flexible mechanical elbow. It lets the drive shaft spin flawlessly and deliver massive torque, even while the suspension is moving wildly up and down over rough pavement. Check out the anatomy here. You have a driving yoke and a driven yoke, connected by this X-shaped center crosspiece, which mechanics usually just call a spider. At the ends of this spider are these precision-machined trunnions that slip into bearing cup assemblies packed with tiny needle bearings. This setup allows the center crosspiece to pivot buttery smooth inside those cups, instantly adjusting the operating angle so your ride stays comfortable and the torque flows straight to the back without anything binding up or snapping.
Just for some added context, if we were looking at a front-wheel drive setup where the wheels have to both steer the car and receive power, a simple U-joint actually wouldn't cut it. We'd have to use highly flexible, constant velocity or CV joints instead. These rely on a really clever assembly of an inner race, a cage, and steel ball bearings. This allows the front wheels to pivot sharply to turn a corner while still continuously soaking up all that engine torque without vibrating the car to pieces.
Finally, we hit section 5, the differential.
Our mechanical journey reaches the very end of the line at the rear axle assembly, where the differential solves our final major problem. It has to take the rotational power coming down the driveshaft, split it at a 90-degree angle to send it out to the wheels. And, this is absolutely crucial, it has to let the outside wheels spin faster than the inside wheels when you turn. If they spun at the exact same speed, your tires would aggressively drag, hop, and skip every time you took a corner. Ultimately, this mechanism takes all that twisted torque, runs it through the axle shaft, and applies it straight to the center of the wheel. The wheel's radius then acts as one final lever, converting that rotational torque into a linear, forward-pushing tractive force, right where the rubber meets the road.
Now, looking at this math in motion is super revealing. You can see exactly how a standard petrol engine relies heavily on steep multi-gear ratios. I mean, look at that overall gear ratio of 15:18, just to match the instant torque output that an electric motor can provide directly. Because an EV motor generates maximum torque right from 0 RPM, its gearbox ratio is drastically lower. That fundamentally changes how modern drivetrains are engineered from the ground up.
Well, I really hope this explainer has shed some light on the sheer brilliance of automotive engineering and maybe leaves you with a deeper appreciation for the metal, the physics, and the leverage that literally drives us forward every single day. From the exploding cylinders in the V8 block all the way to the microscopic needle bearings in the U-joints, it is an astonishing chain of events. So the next time you put your car in drive and pull away from a stoplight, I want you to ask yourself, can you feel that unseen mechanical symphony working beneath you?